When dealing with a three-phase meter base using a 4-wire cable with a ground running to the main service disconnect and the bare conductor isn't needed at the meter or disconnect itself, the question arises of whether or not that bare conductor needs to be terminated. The National Electrical Code, or NEC, provides the guidelines for proper grounding and bonding practices. Although the bare conductor may not be required for the operation of the meter or disconnect, its presence signifies its intended purpose as an equipment grounding conductor. The primary purpose of an equipment grounding conductor, often referred to as EGC, is to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. Without a properly installed equipment grounding conductor, fault current may not be able to return to the source quickly enough to trip the overcurrent device, potentially leading to dangerous voltage on exposed metal parts and creating a shock hazard. Now, to address the question of whether or not to terminate the bare conductor, the NEC generally requires that all equipment grounding conductors be connected to a grounding electrode system. Section 250.24 C1 outlines the requirements for grounding the supply side of the service. It generally calls for the grounding electrode conductor to be connected to the grounded service conductor. A grounding electrode system typically consists of one or more grounding electrodes, such as a ground rod, ground ring, or metal water pipe. These electrodes are intended to provide a connection to the earth, which serves as a reference point for voltage. Although the bare conductor in question is an equipment grounding conductor and not a grounding electrode conductor, the intent is similar to provide a path to ground. Section 250.130 describes methods of grounding equipment and specifically covers the use of equipment grounding conductors. Even if the meter base or disconnect doesn't require the bare conductor for its operation, best practice dictates that it should be terminated. Firstly, if the enclosure of the meter base or disconnect is metal, the equipment grounding conductor should be connected to the enclosure. This ensures that any fault current that might occur within the enclosure is safely conducted back to the source. Secondly, if the enclosure is non-metallic, the equipment grounding conductor may still need to be terminated to other grounding points within the system. This can help to maintain a low impedance ground path throughout the electrical system. Thirdly, even if there are no readily apparent termination points, the bare conductor should be properly insulated and safely terminated in a manner that prevents it from coming into contact with any energized parts or other conductive surfaces. This is important to prevent accidental shorts or ground faults. Fourthly, the NEC also addresses the sizing of equipment grounding conductors in section 250.122. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. It's essential to ensure that the equipment grounding conductor is of adequate size to safely carry the maximum fault current that might occur. Fifthly, it is worth noting that local codes or regulations may have additional requirements or interpretations regarding the termination of equipment grounding conductors. It's always a good practice to consult with local electrical inspectors or authorities to ensure compliance with all applicable codes. Sixthly, consider the potential future use of the equipment grounding conductor. Even if it's not needed at the time of installation, it might be required in the future if the electrical system is modified or expanded. By terminating the bare conductor, you ensure that it's readily available for future use. Seventhly, when terminating the equipment grounding conductor, use appropriate connectors and methods that are listed and labeled for the purpose. This ensures a reliable and safe connection. Eighthly, it is crucial to consider bonding requirements. Section 250.92 covers bonding of equipment grounding conductors. Bonding is the process of connecting together all metal parts that are likely to become energized, creating a lower impedance path for fault current. Ninthly, remember that the main service disconnect should have a proper grounding electrode connection as well, per NEC section 250.24. This is in addition to any equipment grounding conductors that are run with the circuit conductors. Tenthly, the NEC emphasizes the importance of maintaining the integrity of the grounding system. Any modifications or alterations to the electrical system should be done in a manner that preserves the effectiveness of the grounding system. In summary, while the bare conductor may not be directly needed for the operation of the meter base or main service disconnect, it is an essential component of the electrical system's grounding system. It serves as an equipment grounding conductor, providing a low impedance path for fault current. The NEC generally requires that all equipment grounding conductors be connected to a grounding electrode system. Even if there are no readily apparent termination points, the bare conductor should be properly insulated and safely terminated to prevent accidental shorts or ground faults. Consult with local electrical inspectors or authorities to ensure compliance with all applicable codes and regulations. Terminating the bare conductor is a best practice that enhances the safety and reliability of the electrical system. It is always important to refer to the latest edition of the National Electrical Code and any applicable local codes for specific requirements and interpretations. Proper grounding and bonding are critical for electrical safety and should be performed by qualified personnel. It is very important to properly size the grounding conductor. Section 250.122 provides the minimum size requirements for equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. For example, if the overcurrent device is rated as 60 amps, Table 250.122 specifies a minimum size of number 12 American wire gauge copper or number 10 American wire gauge aluminum. If the overcurrent device is rated at 100 amps, the minimum size is number 8 American wire gauge copper or number 6 American wire gauge aluminum. If the overcurrent device is rated at 200 amps, the minimum size is number 6 American wire gauge copper or number 4 American wire gauge aluminum. Always consult Table 250.122 in the NEC for the specific requirements based on the overcurrent device rating. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, typically the neutral. This connection ensures that the electrical system is properly referenced to earth, providing a stable voltage reference and facilitating the flow of fault current. Grounding electrodes can take various forms, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, often referred to as UFA grounds. The type and number of grounding electrodes required depend on factors such as soil resistivity and local code requirements. Section 250.52 specifies the requirements for grounding electrodes. For example, if using ground rods, they must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. If using a metal underground water pipe, it must be in direct contact with the earth for at least 10 feet. UFA grounds must consist of at least 20 feet of bare copper conductor encased in concrete. In addition to grounding electrodes, bonding is another critical aspect of electrical safety. Bonding involves connecting together all metal parts that are likely to become energized, creating a low impedance path for fault current. This includes metal enclosures, metal conduit, metal water pipes, and other metal components. Bonding ensures that all these metal parts are at the same electrical potential, minimizing the risk of electric shock. Section 250.92 specifies the requirements for bonding. For example, metal water pipes must be bonded to the electrical system's grounding electrode system. Metal enclosures must be bonded to the equipment grounding conductor. Bonding can be achieved using various methods, including bonding jumpers, bonding bushings, and bonding lock nuts. It is essential to use appropriate bonding methods and connectors that are listed and labeled for the purpose. The main bonding jumper is a critical component of the electrical system's grounding system. It connects the equipment grounding conductor to the grounded conductor, typically the neutral, at the service entrance. This connection ensures that fault current can quickly return to the source, tripping the overcurrent protective device and preventing electric shock. Section 250.28 specifies the requirements for the main bonding jumper. The size of the main bonding jumper is determined by the size of the service entrance conductors. For example, if the service entrance conductors are number 2 American wire gauge copper or number 1/0 American wire gauge aluminum, the minimum size of the main bonding jumper is number 8 American wire gauge copper. If the service entrance conductors are number 3/0 American wire gauge copper or number 250 kc mil aluminum, the minimum size of the main bonding jumper is number 6 American wire gauge copper. Always consult Table 250.102. C1 in the NEC for the specific requirements based on the size of the service entrance conductors. In addition to the main bonding jumper, there may be other bonding jumpers required in the electrical system. For example, a bonding jumper may be required to connect a metal enclosure to the equipment grounding conductor. A bonding jumper may also be required to connect a metal water pipe to the grounding electrode system. It is essential to identify all potential bonding locations and install appropriate bonding jumpers to ensure electrical safety. Ground fault circuit interrupters, or GFCIs, are another important safety device in electrical systems. GFCIs are designed to detect ground faults, which are unintentional electrical paths between a live conductor and ground. When a GFCI detects a ground fault, it quickly interrupts the circuit, preventing electric shock. GFCIs are typically required in locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. Section 210.8 specifies the requirements for GFCI protection. For example, GFCI protection is required for all 125 volts, 15 amps and 20 amps receptacles installed in bathrooms, kitchens, and outdoor areas. GFCI protection is also required for certain appliances such as dishwashers and washing machines. Arc fault circuit interrupters, or RFCIs, are another type of safety device used in electrical systems. RFCIs are designed to detect arc faults, which are dangerous electrical arcs that can cause fires. When an RFCI detects an arc fault, it quickly interrupts the circuit, preventing a fire. RFCIs are typically required in bedrooms and other areas where people sleep. Section 210.12 specifies the requirements for RFCI protection. For example, RFCI protection is required for all branch circuits that supply 120 volts, 15 amps and 20 amps outlets in bedrooms. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. SPD divert excess voltage away from sensitive equipment, preventing damage. SPD are typically installed at the service entrance and at individual pieces of equipment. Section 285 specifies the requirements for SPD. It is important to select SPD that are properly rated for the electrical system and the equipment they are protecting. Regular inspections and maintenance of electrical systems are essential for ensuring electrical safety. Inspections should be performed by qualified electricians to identify any potential hazards, such as damaged wiring, loose connections, and overloaded circuits. Maintenance should include tightening connections, replacing worn components, and testing safety devices. Regular inspections and maintenance can help prevent electrical accidents and ensure the safe operation of electrical systems. Electrical safety is a critical concern in all electrical work. Following the requirements of the National Electrical Code and other applicable codes is essential for ensuring the safety of people and property. Proper grounding, bonding, GFCI protection, RFCI protection, and surge protection are all important aspects of electrical safety. Regular inspections and maintenance can help prevent electrical accidents and ensure the safe operation of electrical systems. Always consult with qualified electricians for any electrical work to ensure that it is performed safely and in accordance with all applicable codes. The NEC is updated every 3 years, so it is important to stay current with the latest edition. Local codes may also have additional requirements that must be followed. Electrical work should only be performed by qualified individuals who have the necessary training and experience. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent electric shock and other hazards. Always turn off the power before working on any electrical equipment. Use appropriate personal protective equipment, such as rubber gloves and safety glasses. Follow all safety procedures and guidelines to ensure a safe working environment. The grounding electrode system should be properly tested to ensure that it is effective. A ground resistance tester can be used to measure the resistance of the grounding electrode system. The resistance should be low enough to allow fault current to flow quickly back to the source. If the resistance is too high, the grounding electrode system may need to be improved. This can be done by adding additional grounding electrodes or by improving the soil conductivity. The equipment grounding conductor should be properly connected to all metal enclosures and other metal parts that are likely to become energized. The connections should be tight and secure. The equipment grounding conductor should be sized according to the requirements of the NEC. The main bonding jumper should be properly installed and sized according to the requirements of the NEC. The main bonding jumper should be securely connected to the equipment grounding conductor and the grounded conductor. GFCI protection should be provided in all locations where it is required by the NEC. GFCIs should be tested regularly to ensure that they are functioning properly. SI protection should be provided in all locations where it is required by the NEC. SI should be tested regularly to ensure that they are functioning properly. Surge protective devices should be installed to protect sensitive electrical equipment from voltage surges. SPD should be properly rated for the electrical system and the equipment they are protecting. Regular inspections and maintenance of electrical systems are essential for ensuring electrical safety. Inspections should be performed by qualified electricians to identify any potential hazards. Maintenance should include tightening connections, replacing worn components, and testing safety devices.